It's great to be here. I'm Mihir Kulkarni. I'm a postdoctoral researcher at the Norwegian University of Science and Technology. In this talk, I wanted to share with the community some of our research that we're doing at the Autonomous Robots Lab in NTNU. This research ranges from all aspects of robotics to autonomy for flying vehicles and beyond. And just to motivate the kind of missions that we do and the kind of environments we want to deploy our robots in, these are some representative robot deployments. This is from 2018, where we had a DJI Matrice robot autonomously exploring underground tunnels, caves, mines, essentially GNSS-denied confined environments. This the same application, but with an antibiotics animal robot that we had partnered with ETH Zurich for. So this was research that was done in the context of the DARPA Subterranean Challenge. The clips you see currently are actual deployments from that challenge, which our team won. So these are the some of the environments that we care for and we want to operate in and want to develop resilient autonomy for. And what's the challenge? What's the challenge? This is the starting point of my talk. So we worked a lot towards having resilient systems that worked well enough in these environments, but then there were still some problems. They were not sufficiently resilient. What had happened was that the development in this field of autonomy has happened based on the sense think act paradigm, where typically you see a compartmentalized development of modules, where initially there's a slam frame. I don't know if my mouse is, yeah, initially there's a slam framework which takes in data from the sensors, gets an estimate of the environment where the robot is in the environment, a dense mapping solution that builds representations within which a path planning algorithm then plans what the robot should do next in order to achieve its goal, be it exploration, be it inspection of surfaces, be it any other user defined objective. On the planned path, a low level controller operates to actually uh, motion control happens to smoothen the path, and a low level controller then tracks this with finally the actuator commands. So, what's the challenge with this? The development of these modules has happened in a way, or at least in our case, had happened in a way in which each of these modules depended on the other ones being correct all the time. So in the case where the SLAM module failed, in this case, purely LiDAR-based state estimation methods are prone to inconsistencies. They drift, they struggle with self-similar geometries where they cannot localize well. They struggle in the case of where there are obscurants in the environment, such as smoke, dust, particulate matter. And naturally, they have some sort of drift in large-scale environments. Because of this, dense mapping also struggles because when there are hard to perceive obstacles such as thin branches, twigs, wires, cables, etc., they're not mapped because the mapping resolution is directly related to the available computation on board and memory. And in the drifting state estimates also cause an inconsistent map through which if a planner plans paths assuming a map is free, it may not be, and the robot might try to go through an obstacle. And then the control has to work with drifted and incorrect state estimates, which is in itself again a problem. So we wanted to propose an evolved approach where we interleave these layers in a manner that each layer tries to perform the best it can, and the layers that depend on it don't assume that the data coming in from, let's say, upstream here is always correct. So they are resilient to errors, failures of state estimation, errors in the planned path, and so on. So what do we need to achieve this? We realized we needed two things. We needed good tools to achieve this, and we needed good methods. So in this talk, the first focus is on vision-driven learned navigation, which is able to enable safety, local safety for the robot to go from point A to point B, despite erroneous state estimates or erroneous paths or paths going through things. So for tools, we needed fast, accurate simulation, versatile rendering to simulate the sensors, and the ability to support diverse platforms. On the side of methods, we need methods for safe navigation and control. We need better multimodal sensor fusion so that the SLAM module itself operates well all the time. And we want to be able to deploy the same kind of autonomy stack across different robot embodiments, be it a flying robot, be it a ground robot, be it an underwater robot, with very minor robot specific changes to this autonomy stack. So coming to the side of tools, the first thing we needed was a lot of data to train our neural networks. For this, we built the aerial gym simulator, which is a specialized multi-rotor simulator that is now open sourced and is widely adopted. It's built over the NVIDIA ISEC Gym physics simulator. So we provide out-of-the-box high-level controllers and low-level controllers, and also introduce a custom GPU accelerated rendering framework so that the users have complete control over what kinds of sensors they're able to simulate. So the robots that are provided out of the box with the simulator have a very diverse range. They go from a planar quadrotor, fully actuated octarotor from literature, a random configuration. Another niche configuration, which here is a robot with compliant arms made of silicone. So we have a realization of this platform, and this can bump into things and squeeze through narrow gaps. And another one, which is like a flying snake from literature. So these are provided out of the box so that the users who want to experiment with different kinds of systems already have a prior example and they can build upon top of this. High and low level controllers that range from position control, velocity control, body rate, attitude, acceleration are all provided, and these are implemented from very common literature using PyTorch, such that they can be parallelized on the GPU. To the extent that we can have 65,000 parallelly simulated robots, or up to a million actually, on a laptop computer. So these controllers provide a wrench to track, and this then needs to be allocated. The typical way for doing this is providing a pseudo inverse, Penrose pseudo inverse of the allocation matrix. That is, I believe, the same way PX4 does it for standard configurations, and this is also implemented in PyTorch along with motor simulation. And this is how the entire simulation pipeline goes, that the physics engine provides the robot state, geometric controllers use the state and the user provided or an RL algorithm provided set point command, provide a wrench that is then distributed to thrust commands, motor simulation is performed, and this is applied back into the physics engine. So this solves the physics and control aspect of our proposed open source simulator. We also have a customized rendering framework that's based on NVIDIA Warp, where we are able to do very fast raycasting. So ISEC Gym has already provided a rendering engine with their simulator, but it was too slow for our use, and with our and it was also closed source, so we didn't know what was happening under the hood. So with our implementation, we are able to get about an order of magnitude speed up compared to the closed source solution provided with the physics engine. So for doing this, the environment is represented as a set of triangle meshes. The vertex information is consolidated into a list, and the states of these meshes in the physics engine, that's the NVIDIA's physics engine, and our custom representation is matched such that we can perform raycasting. With that, we're then able to simulate sensors with custom field of views, custom projection models. So here are some examples with a warp-based camera sensor with a depth camera, where we can simulate it for depth, surface normals, segmentation. And now, since we have control over the entire representation, we can get more niche information, such as face indices of every mesh face. We actually use this for doing inspection to maximize the volume, maximize the number of unique surfaces seen by a robot. And then also, of course, dome lidars, which are not possible to simulate using ISEC Gym. We can also simulate noise, such as stereo shadows that are commonly seen in stereo pair depth camera. So if you see here, uh, there is a shadow on the left side of every object, and that's typically what happens when visibility constraints. This happens because of visibility constraints, where one camera can see a region in a stereo pair, but the other cannot, and there is, of course, information that's not present, and this can be simulated very well. And this gives us a very high rendering throughput. So for low resolution sensors, we get about an order of magnitude speed up. For high resolution sensors, we're able to reach the same speeds as NVIDIA ISIC Gym, but much better on the GPU RAM side. So we are able to simulate more environments. With this, we have a simulator ready that we then use to train policies for navigation, set point tracking, for vision-based navigation, and also for low-level motor control to track positions. So all of these are trained on the simulator. Oops. All of these methods are trained on the simulator, and they are deployed on real-world platforms so that we have a very good sim-to-real transfer process. The process for training each of these policies is also open sourced. So if you check out our repository, you'll be able to reproduce these results. And we're also porting our simulator to, so the features of our simulator to be compatible with the newly supported or the newer and currently supported ISIC lab, and this is going to come soon. So with this in place, we also wanted to try to use our neural networks directly on PX4. So this is generally the PX4 standard control cascade, where we have position controller, then attitude rate controller, and a mixer. So we take out this block and we replace it with a neural control module. And this is just an inference script that runs on the embedded PX4 platform. So we're training a multi-rotor in simulated environments, converting them to formats that can be flashed onto embedded autopilots, and then we validate on real hardware. So this is an example of the embedded PX4 neural mode running. And this is also contributed as an experimental feature to, I think, version 1.17 in PX4. So you can try it out. You can train your own neural networks for robots in aerial gym and deploy them on your platforms. So with this, we wanted to go a step further. We also wanted to see what we can do in terms of robot design. So we have very fast simulation, but can we also improve designs of the robots that are doing certain tasks? So this was led by a postdoc of our group, and we defined that for this problem we had two tasks of interest for us. The first task A, was a set of gates that are minorly deviating from each other, and a task B was a distribution of gates with a certain profile where most of the gates are one behind another and then they suddenly change. And we wanted to see if we can evolve designs that outperform standard airframes for each of these tasks. So the method proposes that we use a Bayesian optimization for airframe parameters. This is then trained using a neural network policy to complete these tasks. And then we then evolve designs and train controllers for them such that we're able to optimize for the task at hand. So this is an example of various designs being simulated together for the task A at least. For the task B, which was a bit more extreme, we actually built the design that we evolved, and this is how it performs in the real world when we deploy it. The dotted line here in the graphs is that of the simulated robot for the same mission, and the solid line is for the real robot, and they're pretty close to one another. So moving on, so from the tools side, we now have a reliable simulator. We have ways to get neural networks on embedded platforms. And we can also change our robots to optimize them for the tasks at hand. Now we move on to the methods that we want to develop to enable safety on the robots. So what do we want to do? We want to have collision-free flight in cluttered environments. We want to reduce reliance on maps and reduce reliance on accurate state estimates, as they may be erroneous. We want to be able to we want to be robust to real-world sensor noise, have good Sim2Real transfer, and generalize across diverse environments. For that, we need to have good representations because we can't directly take images from simulation that are perfect, depth images that are perfect in simulation, train neural networks on them, and expect them to work directly in the real world without being able to faithfully model the real world noise. So now we want to develop representations that will help us accelerate this process. For that, we come up with an idea of collision images, where in planning, there's a typical approach where a robot used to be considered as a point mass, and everything in the environment used to be inflated by the size of the robot. But this, since we're not using maps, this is difficult to do, and we want to use only images. So this is a bit challenging because we want to inflate the images to account for the robot size so that we know along each pixel what is the collision-free distance a robot can travel. So for that, we devise a novel method where we perform edge detection. We project a point to the corresponding 3D location in the depth image. We render a virtual mesh the size of the robot in this virtual environment, overlay this rendered virtual mesh with the original depth image, and then we get something called a collision image, where each pixel is the collision-free distance that can be traveled along uh, uh, along that direction. What this helps do is it, for flat surfaces normal to the camera, uh, it brings the surface closer, but for very thin objects, it kind of inflates them sideways as well. So this reduces the complexity of the data that is present in the collision image, because now if you look at the next one, here you see a chair on this input image, but the information here is actually not useful because there is no point knowing that the robot, there is free space here because the robot wouldn't go through it anyways. So then the collision image gets rid of that free space. So our image that we want to consider becomes much simpler. So to be able to have this make use of this representation, we collect a data set from simulated and real world images, train an encoder that compresses it into a latent representation 1,000 times or more smaller than the image that has all the information about the collision image. And we use this to train a navigation policy that uses the robot state, the compressed latent representation from the depth image that has the collision information, and provides velocity commands such that the robot can navigate the environment safely. This is then put in the aerial gym simulator, and 1024 parallel environments are used for training an RL policy. And we have simulate noise and disturbances, match the response of the controller, and so on. And this is the result that we get. We now have a policy that is able to navigate these environments when it's provided a vector to the goal location, the current state, and the depth image. And then it's commanding velocities and yaw rate to the robot such that it can traverse this environment, and it's quite robust to the real world sensor noise. This experiment actually was a bit of a deviation from the training because we restricted its vertical velocity, which was not how it was trained. So when we don't do that, the robot takes a more natural path to, in fact, go over the obstacles, and a more reasonable and a safer path to the goal location. So we are also, the policy is also robust to these kinds of changes when during inference, and these are not what it was trained for. In addition to this, we have also open sourced our work with composite CBF based last resort safety that provides uh, certifiable safety to the platform in a way that it can it's a CBF based control layer where user provided acceleration commands or an algorithm provided acceleration commands are corrected by the safety filter such that the robot is commanded necessarily command that lead it to a safe region in the environment. This was evaluated on Model AI Voxel 2 mini platform on the in the left video. On the right, it was evaluated using an Ouster lidar on a much larger platform with deployment on an Orin NX compute. So now we come to with a solution for safety on the lower level vision based navigation. We now come to improving the state estimation and the planning side of our autonomy stack. So as discussed, we have quite some challenges with self-similarity because the LiDAR-based methods have failed or have a significant drift. A lack of visual texture is, of course, a problem for vision-based estimation, and obscurants such as smoke or dust don't help. So a new method was proposed where multimodal fusion can be performed between a LiDAR, a camera, radar, and IMU, where we can produce IMU rate odometry or the graph rate odometry and also build an online map that continuously updates itself. To do this, we use a factor graph based approach where nonlinear optimization is performed from cost terms that are derived from the LiDAR, radar, camera, and the IMU. And these are some of the results uh, of the deployment of this method from a year and a half ago in an environment filled in a university corridor environment filled with smoke. So as you see, the person with the camera is walking barely a meter or a meter and a half away from the robot, and the robot is not quite visible. The lidar has this challenge where the lidar sees only about a meter or two, and is pretty much a purely lidar based method fails in this environment. But the fusion of radar in this estimation architecture helps it retain robustness, and we're able to estimate the trajectory of the robot, build a map using the data for a much longer part of the mission. And this robot now exits the smoke filled corridor and goes back to the starting location in a much clearer zone. And then, of course, I'll just, in the interest of time, just briefly say that we have a universal planning algorithm across robots where we can plan for exploration and inspection for aerial, legged, and underwater robots. And this is also open sourced as GB Planner, graph based exploration planner. This all comes together in an embodiment which we have recently released as Unipilot, where we want to enable GPS denied autonomy across robot embodiments. So we've built a module that has a LiDAR, a bunch of cameras, a radar, an IMU, a time of flight sensor, and a GPU enabled computer. This this module is then deployed first on a multi-rotor, a legged robot, and a hybrid fixed wing platform. And in this mission, you can see, equipped with this module, we are able to perform exploration of uh, a mine in Norway, where we don't know anything about the environment before we deploy. In this part of the video, the robot with the same module is performing inspection of a ballast tank inside a ship. So this is a process that's required to ascertain the health of the ship, and this can be done autonomously uh, using our autonomy stack. And of course, we are also evaluating this in fast flight, where we reach up to 15 meters per second, and we're able to estimate the robot position and build a map for at the speeds. And the same can be transferred to a legged robot for exploration. And we also perform odometry evaluation using purely the radar and IMU on this fixed wing platform, a hybrid fixed wing platform, which we are currently flying in a multi-rotor mode. And there is work ongoing to have radar-based odometry estimation directly on the embedded flight controller. And all of the, or most of the results I've shown in this presentation are already open sourced. The ones that aren't, we plan on releasing them soon. And you're more than welcome to check out these results repositories and let us know if these work for you or open any issues. These are the publications that go alongside these contributions. And that's my presentation, and I'm happy to take any questions.
Lovely. Excellent. Thank you, Mihir. Are there any questions in the group? Questions? Yes. Microphone is all yours.
Great talk. Thank you so much for sharing all the progress you have made, especially with Isaac Sim, Isaac Lab. Not a lot of people use it, especially when it comes to aerial platforms. My question was specifically with respect to adding a custom airframe. Like if we have our own airframe, how would you suggest we integrate that with either Aerial Gym or when you move to Isaac Lab? That.
Thank you for the great question. So this is actually a challenge for someone starting out with their own platform and you trying to use a simulator. So what is important for simulating custom robots is firstly a few things. You need to match the want to have accurate dynamics, or at least match the responses. So you want to have accurate measurement of mass. You want to, so you can, these are all URDF files currently, the ones that are provided. So if your robot is represented as a URDF file format, it's great. It can be read by the simulator. You need to have accurate mass in your robot, accurate inertia in the for the robot. And then for actuators, you need to specify what are the thrust coefficients, the thrust to torque ratios, or the torque coefficients, the time constants for increasing RPM, decreasing RPM. And then for the controllers, if you only want to do low level control, motor control, this is enough. But if you want to have the robot track velocities or track accelerations, you have to perform controller tuning, where you tune all of these constants here that are specified directly in the configuration file. So it's just replacing values with those that work for your robot.
Thank you. I had a second question. Is that okay? It was more with respect to the challenges that you faced in terms of Sim2Real transfer. Did you have to you test it in the real world, you realize some things didn't work and go back? Like what were some of the things that you had to go back and tune more to make it more realistic, basically?
To be honest, only these things I've mentioned. Nothing else. If once we had to improve these a bunch of times, but at some point for the newer platforms, once we determined these correctly, we didn't have to go back to simulation to change things. At some point, then it becomes a reward function tuning problem. So accurate estimation of parameters is quite important.
Here you go.
Okay, somewhat unrelated, but the drone snake. Okay, have you ever simulated that? Are the hinges actuated? I just need to know more.
The flexible drone?
Yeah, the snake-shaped drone.
Oh, the snake-shaped drone. We've simulated that, but we haven't realized it in the real world. This was literature from Dr. Moju Zhao from University of Tokyo many years ago, and we thought it was an interesting platform to include. So this one is there are other people who are more familiar with this kind of a system than we are, but we've included the system to provide an example. The one on the left, the Morphe robot, is actually something we've built in the lab. which has silicone arms and encoders in the arms.
I guess my biggest question was: are the angles between the rotors, are those actuated or are they just loose?
Which
Do you know?
which of which
On the
platform?
I just want to know about the snake. So
Okay.
like, can it be like a floppy snake with rotors on it, or like do we have hinges, or is it like
Yes,
is it actuators?
Yeah, so exactly. There is a 2 degree of freedom joint here that can be actuated.
Okay.
That's how it's modeled. I mean, the realization, it then once you realize the robot, it then depends on how the realization is constructed. But that's how it is currently. So it's 2 degree of freedom joints. Everywhere you see a cord.
All right, thank you. Anyone else? Oh, good. All right, let me start here and then we have enough time.
Just a quick question. What was the fastest you were able to fly with that LiDAR plus radar system while successfully detecting and avoiding things?
Can you say the last part
So
again?
you had a combined system with the LiDAR and the radar system. What was the fastest you were able to fly while detecting and avoiding things? Just
So these were unconnected research work. So one is estimation, one is collision avoidance. So on the side of collision avoidance, the fastest we've gone is actually with a depth camera, and that was about 2.8 meters per second in cluttered corridors.
gotcha.
And for state estimation, we've gone up to 10 meters per second or up to 15 in that video in relatively open corridors with we didn't have to avoid things at that high
Understood.
speed.
Thanks.
All right, let me navigate towards this next person. It's you, because I remember you.
So my question is, what visualization did you use for those plots at the end? And is that all real time or was that in post?
Which part of the Unipilot or
Like all the way at the end when you're going through the tunnels and stuff.
let me check.
Like all the rainbow plots. Yeah.
These?
Yeah.
This is Arviz and Adobe Premiere Pro for putting things together.
And that's all real time.
Yes, all of it.
This one or this one?
In this video, this was from 1.5 years ago. This was run offline, but what we have in the Unipilot video is all real time. This is from some months ago. So.
This guy. We got more questions over here. Let me just change batteries here. All right, Fernando.
Now that the microphone is supercharged. Thanks for the talk. You started mentioning that how we need to replace some of these traditional approaches that we have been doing for some sort of end-to-end learning system because the performance will be better. That's a story that I've heard a lot from academia. I yet have to see an example where you perform better than traditional systems, model-based systems, except for a couple of like situations in like racing, for instance, where you have a control interface and your variables are not changing that much. I'm curious if you had an example, a concrete example where these systems are performing better than traditional model-based systems.
Just to clarify, I don't personally think an end-to-end system would outperform the hierarchy of modules for complete autonomy. At least the way we are applying it.
But you're like bypassing. You're doing sensors to directly like a learned representation that you're going to be using for autonomy. Bypassing like SLAM and mapping and path planning, which are the traditional cascade approaches.
So the classical methods such as model predictive controls or these work very well on robot state, but they struggle when high dimensional sensor data such as images are to be used. This is where data driven methods such as learning based approaches from reinforcement learning or classification based methods kind of work very well, where you are able to have neural networks encode or extract features from data that you wouldn't otherwise be able to hand engineer for the classical methods such as MPC for collision avoidance. So this is where we believe the strength of learning-based method comes in.
Do you have any concrete examples?
I mean, for example, I would struggle to formulate a method where we use directly the image and an MPC solver where the state of the system is 1,000,000 pixels and 13 for position, orientation. It would be very difficult to define a function of as to the evolution of this state.
Thank you.
Good. I was gossiping right there. Sorry. Took me a minute. Who else? Here we go.
As I was watching the animation, as you were going through the various configurations possible, saying what's the optimal design, that's pretty cool, right? I'm just curious, as you're going through that, does it take into account, for example, if you have one rotor which is sitting in the output of another rotor in terms of that design, due to the loss of efficiency because the higher velocity coming off of is that a part of that sim?
Yes, the rotors for the placement, they were modeled as elongated cylinders, not just the discs, and collision checking was performed to see that no two cylinders were intersecting. So at least the airflow below a rotor would be clear
Yeah,
for
cool.
this purpose.
Thanks.
All right. Think I got time for one more. Ben.
Stealing mics. Thank you so much. You mentioned adding a module inside Pix4 to actually run inference on neural network to replace the existing control cascade. The control cascade in Pix4 is running at different frequencies, so like rate controller, very high frequency, position controller, much lower frequency. How do you match this on the neural mode? Is it running at multiple frequencies of inputs, or is it the lowest or the highest?
Can you give a more specific example? Can you repeat this with an example?
When you substitute the entire Pix4 control pipeline with your neural network, basically, what is the input and what is the frequencies is it running? Is it running at the output of the odometry topic, or are you taking the high frequency vehicle rate, vehicle angular velocity topics and mixing it? Is it multi-rate or is it single rate?
So in this case, we have one neural network which replaces these three modules. So in this case, for the offboard mode example, we replaced whatever was in the offboard mode with a neural network. So at the frequency at which it was called, the neural network runs at that same frequency. So just to give a number, the inference of this neural network on an M Robotics PixRacer Pro unit takes about 100 microseconds. So it's not so expensive. It's not that different from the control loop that was already running for the offboard mode with the classical approach.
Thank you so much.
All right. Thank you so much.